Photonic anomalous Floquet insulators are materials with exotic electronic properties that emerge when they are periodically illuminated by light. In these systems, the time periodic driving, like light pulses, alters the material's electronic structure, creating unique states that wouldn't exist otherwise. These states, called Floquet States, allow electrons or photons to move along the edges of the material without scattering, even if the material itself is disordered. For example, these edge states can conduct electricity or light with high efficiency, defying classical rules of conductivity. Imagine turning on a strobe light in a room full of obstacles and suddenly being able to walk through it effortlessly, as if the obstacles disappeared. These materials are exciting for applications in quantum computing, optoelectronics, and robust light-based communication systems, as they offer new ways to control and manipulate quantum states using light.
Photonic anomalous Floquet insulators are a class of materials whose unique electronic or photonic properties arise from periodic driving, such as illumination by a time-dependent light source. These systems are characterized by Floquet states, which are time-periodic solutions to quantum systems driven by external fields. Unlike static materials, the periodic driving reorganizes the material's band structure, creating new energy states and allowing topologically protected edge modes to form. A photonic crystal illuminated by pulsed lasers can exhibit topological edge states where light is confined to the edges and propagates without scattering. Imagine turning on a disco strobe light in a crowded room, and suddenly you can glide effortlessly along a designated path while avoiding all obstacles, a result of the dynamic reorganization of your environment. Floquet theory describes the behavior of quantum systems under periodic driving. When a material is illuminated by time-periodic light, the Schrödinger equation is modified to include the time-dependent Hamiltonian. The periodic driving effectively creates quasi-energy bands, analogous to electronic band structures in static materials, but defined in a Floquet space. These bands allow for the emergence of exotic states, such as topologically protected edge modes, that do not exist in the material's equilibrium state. A semiconductor exposed to high-frequency laser pulses exhibits Floquet quasi-energy states, where electrons can occupy unique energy levels not found in the unperturbed material. Floquet states are like stepping into a rhythmically shifting maze, where the walls periodically rearrange to create new paths that weren't there before. The periodic driving in Floquet insulators induces topological invariants, which define the material's electronic. In photonic systems, these edge states allow light to travel unimpeded along the material's boundaries, even if the bulk is disordered or contains obstacles. In photonic anomalous Floquet insulators, edge states enable light to travel around sharp corners or through highly disordered materials without losing energy. Edge states are like guardrails on a winding mountain road, ensuring that your journey remains smooth and uninterrupted regardless of the road's condition. Anomalous Floquet insulators exhibit unique behaviors that cannot be explained by static topology alone. Unlike conventional topological insulators, they derive their properties entirely from periodic driving. This enables them to support edge states even when the bulk topological invariants of the system are zero, a phenomenon exclusive to driven systems. In a periodically modulated graphene-like lattice, Floquet edge states can emerge in an otherwise topologically trivial material, highlighting the role of light-driven dynamics. Anomalous Floquet behavior is like a dull, ordinary room transformed into a dynamic playground when illuminated by rhythmic, pulsating lights. One of the most exciting features of photonic anomalous Floquet insulators is their robustness against disorder. The topological nature of the edge states ensures that photons or electrons remain immune to backscattering, even in the presence of defects, impurities, or irregularities in the material. In a disordered photonic lattice, edge modes can still guide light around obstacles or imperfections, maintaining high transmission efficiency. Disorder-resilient propagation is like being able to ride a train through a chaotic, debris-strewn landscape without feeling a single bump. Photonic anomalous Floquet insulators can be engineered using photonic crystals, periodic structures that control the propagation of light. By modulating these crystals with time-periodic light, researchers can create custom light paths and manipulate photons with unprecedented precision. This ability to dynamically shape and guide light is a key feature for applications in optical computing and quantum communication. Photonic Floquet crystals are like programmable highways for light, where traffic patterns can be controlled and optimized in real time. The robust, topologically protected edge states of photonic anomalous Floquet insulators are highly desirable for quantum computing. Additionally, periodic driving allows researchers to dynamically reconfigure quantum systems, creating adaptable architectures for quantum information processing. Example: Floquet engineering has been proposed to create stable qubits in photonic systems, leveraging their immunity to environmental disturbances. Analogy: using Floquet states in quantum computing is like having a perfectly insulated data cable that ensures error-free communication even in the most chaotic environments. Photonic anomalous Floquet insulators provide a platform for designing highly efficient optoelectronic devices. By controlling light-matter interactions through periodic driving, these systems can achieve enhanced light confinement, efficient energy transfer, and low-loss photonic circuits. Their dynamic nature also allows for reconfigurable devices, paving the way for next-generation technologies. Example: Floquet-engineered photonic chips could enable ultra-fast, low-power optical switches for data centers and communication networks. Analogy: optoelectronic devices based on Floquet engineering are like adaptive traffic systems that optimize flow dynamically, ensuring maximum efficiency under changing conditions. Studying photonic anomalous Floquet insulators provides insights into non-equilibrium physics, a frontier of modern science. These systems mimic astrophysical phenomena, such as the behavior of particles in intense electromagnetic fields around pulsars or black holes. By exploring these materials in the lab, scientists gain a better understanding of how quantum systems behave under extreme, time-dependent conditions. Example: theoretical studies of Floquet systems help model how charged particles behave in the rapidly oscillating magnetic fields near neutron stars. Analogy: investigating Floquet insulators is like creating miniature, controllable versions of cosmic events, bringing the mysteries of the universe into a laboratory setting.